In this video we'll look at bias. So it's the same schematic as earlier, and last time we looked at the signal value, but today we'll be looking at the bias value. So if you look at the bias value, is the average value, which is here. So if I look at the average value, it's 900 millivolts because that's the input I gave it. And if I look at the bias value here, it's 225 odd millivolts. So if I look at the difference of the two, it's a little more than 600 millivolts. If I look at the second plot, then if I look at its control and left click, I see that the input average that I gave was 700 millivolts, and if I look at this one, it's 66 millivolts. So again a difference of some 600 odd, 650 odd or less than that millivolts. So the next thing we had seen was basically if I no longer directly connect the input and use the bias from there, but I'm also generating the bias here. So this is 10 volts. This is a resistor divider, so that's 0.9 volts here and 9.1 volts here. This is a resistor we have put. It could be in kilo ohms, so we can change that also. So we'll see. So we'll change it to 0.9k and kilo ohms, and I'm going to put a capacitor here. It can be any value capacitor for starters. What I'm trying to do primarily with the capacitance is disconnect the bias from here to the output. So if I just add a cap, so I can rotate the capacitance and I can put it here. And I have to put a value, so let's say I just put a microfarad of capacitance. So now if I see the voltage here and the voltage here, I can see that there is a signal wise attenuation, there's a phase difference, but if I look at the bias, this was 900 millivolts, and if I look at this, that's also very close to 900 millivolts as I'm setting it up here. If I change this DC offset to 0 and then run the simulation, then it suppose has a DC offset of 0, but what is coming across is still the bias set up by this. So now I'm basically independent of the input, but I'm getting an attenuated signal. So there's something called add plot pane, so this will let you see both of them simultaneously, and you can see that they are not quite in phase, they are a little off, and that's because of the effect of the capacitance of this leading lagging sort of thing. You're getting some sort of filtering. So if you want to figure out what that is, you can use the AC simulation. So here's the AC simulation. I'm just going to copy this. I could make it a spice directive, but I'm just going to copy it and leave that alone, and I'm going to paste it here. So I'm going to switch to AC analysis, and I'm going to run a sim. So one of the questions is, what does the AC sim results mean? So let's try to understand that. Window. So this says that the input is 1. If I apply an input of 1, the input 1 is 0 dBm, which is 20 into log 10 of 1 is log of anything. Log of 1 is 0, so that's 0 dBm. And if I look at, there are two things I see in this one. That's a dotted line that's going down, and one that is a solid line that's going up. My frequency, I think it's zoomed in, zoom to fit. Oh, sorry, clearly I didn't run the simulation myself. So a megahertz. So what I see is are two curves, and one is the amplitude curve and one is the phase curve. And if I select this, it tells me the amplitude value as well as the phase value, but it also tells me which cursor I am on. So if I switch to this is my phase plot, and if I put the dot on that, that's my amplitude plot. So it tells me that at low frequency basically it's cutting it off, and as the frequency is increasing it's making it through more and more. So if I look at where it's become fairly good, I'm getting this at 1 kilohertz, so maybe around 2 or 3 kilohertz is where my signal is actually coming through nicely. In the class we had left this as 9 ohms and 7 ohms, and that's why the pole was so bad. Okay, so it's good that we have seen it. So now even if I put something like 100 micro or maybe even 10 microfarads and run the simulation, then I can see that even at 100, even at 100 hertz, your signal is actually coming through. So let's do that. 100 hertz, we already have 100 hertz, and instead of the AC, we'll just do the transient. So now I see that my input signal, well, I'll just put it at 0.9 so we can compare the two. So bias is a little bit off, but my amplitude is pretty good, and there's still some slight phase difference that I can see. And if we go back to the AC plot, and look at this, then you can see that at 100 hertz, if I change this to 100 hertz, I see there's a small phase difference between the input and the output. So, and that basically tells me that I'm seeing that phase difference of 11 degrees or so, a period being 360 degrees. I'm seeing a small difference, delta, between what is the signal I'm applying at the input versus what I'm actually getting here. Okay. So next we looked at how do we increase the gain of the stage. So I have a gain. So if I look at the output, then I can see that around 100 hertz or more, now this is 200 hertz, I'm getting a gain of 18.89 dB. So do you remember 20 dB is a gain of 10, and this is 19 dB, so it's 1 dB less, so that's like 10% less, so around a gain of 9. So we're getting around a gain of 9, and if we wanted to get a larger gain, the one way to do it is to leave the DC part as it is and just add a large capacitor. So if I just add a large capacitor, I can just say capacitance, I guess, here. And as I increase this capacitance, my gain starts going up. So if I put this is a grounded capacitor, so I can get a fairly large electrolytic capacitor, and if I put that, then my gain has gone up almost by 20 dB, which is another 10, so it's like around 90 or so. So if I feed 0.1 volts, and that's probably too much, and because it's 90 times that, so I'm trying to get a 9 volt output, that's a bit too much. So I'm going to reduce this, so let's say 0.05, and then, oh, that's an AC sim. So if we go back to our transient simulation, we feed in the signal and we run the transient simulation, and we look at the output, well, you can see that it's distorted, it's hitting the top because I only had a DC voltage of around a volt, about 2 volts, so 4 volts is too much, so it's looking fairly distorted. So I need to, this part is something you cannot figure out from the AC simulation. Still not too distorted, so I can increase it a bit more. Okay. And still doesn't look too bad. So in real circuits, you would not rely on the input bringing the bias that you need. You would set up the bias yourself. You will AC couple the input, and then you will create the amplification that you need. And you can get a significant amplification, as you can see, out of the device, as long as you are careful about the kind of swing you're getting and the kind of output that you need. And that's what that's what is a biasing part. It sets it up in a place where it can do what it needs to do. So the model that we had, we are just going to modify a bit. We had an later, and now we are going to put a small voltage source in series with it of 0.65 volts or 0.6. It's a round number. It gives us an approximate result, and then we can always refine it from the simulations. And then a narrator, and as we learned last time, the resistor. I'm going to start using the European style of drawing resistors, which is just a box. Saves time. So this is the base, this is the collector, and this is the emitter. And just to remind you, RE is VT, the threshold voltage, as a function of temperature. That's why we write VT divided by the current that we have. We call it IC. It's a collector current, but it's the current of the circuit. So VT is KT by Q, and it's not necessary to remember it's KT by Q, except that it's proportional to temperature. So this is 25 millivolts at room temperature, which means if I had a current of 1 milliamp, then the resistance that I expect to have at that emitter is 25 ohms. Roy pointed out that one way to check if the BJT is functioning or not, the bipolar transistor is functioning or not, is to just sort of where you have your device, you have your transistor, just to bring something that sort of heats it up, maybe a soldering iron near the top, and you would see that as the temperature increases, this VT increases and the resistance actually increases. So this resistance would be increasing. That means the gain of your circuit, whatever the gain was, would actually tend to drop. So if the gain of your circuit is dropping, then you know that your your BJT is actually functioning, and well, it tells you it's also a BJT device versus a MOSFET. In case of the MOSFET, as the temperature increases, your gain will actually increase, and you can have a thermal runaway. So that's not a problem with bipolar junction transistors.